Welcome to episode 4 of Navigating Metric Space Topology. Recall that in the previous episode, we were talking about convergence in a metric space. Now I want to switch gears and talk about what's called the limit point of a sequence. And here, you can really work in any metric space, but let's work in the real numbers with the Euclidean metric for the moment. And let's say we have a phenomenon that looks something like this. We have some point A here, and we have some point A prime here, and our sequence looks something like this. We have A sub 1 here, and maybe A sub 2 here, then A sub 3 switches back over to here, then A sub 4 here, then maybe A sub 5, then A sub 6, and what we have is A sub 7 here, A sub 8 here, A sub 9, and so on, where the odd terms, perhaps, are converging to A, and if you look at the even terms, they're converging to A prime. Well, if you look at the entire sequence, A1, A2, A3, and so on, then the sequence is not converging to anything. And I guess I should really point out that when a sequence does not converge, you say it diverges. So if I look at the entire sequence, there is not a single real number that the terms of the sequence are approaching, so the sequence is gonna diverge. But certainly A and A prime still kind of behave like the limit of the sequence, in the sense that there are infinitely many terms of the sequence getting closer and closer to A, and there are infinitely many terms approaching A prime. So these two points are called limit points of the sequences. To define limit point a bit more rigorously, what we say is that A is a limit point of a sequence A1, A2, and so on if there exists a subsequence A sub n1, A sub n2, and so on that actually converges to A. And I suppose I gotta define what a subsequence is. If I have terms of a sequence like this, a subsequence is obtained by taking some term of a sequence, then moving to the right, you only move towards the right, taking some other term, moving to the right, taking some other term, and so on. And you do this infinitely many times. So here when I say n1, n2, the indexing terms of the sequence, these are going to be the numbers satisfying n1 is strictly smaller than n2, then strictly smaller than n sub 3, and so on, where n1 can start at 1 or larger. So for example, in this picture, a1, a3, a5, this would be a subsequence, and it converges to some point. So here it converges to A, that's a limit point. And we also have a subsequence a sub 2, a sub 4, a sub 6, and so on, that converges to A prime, so A prime is a limit point as well. I emphasize one more time that the limit point can be defined in any metric space, but starting now let's focus our attention on real sequences. So every term is a real number, and let's additionally assume that it's bounded. So we have an upper bound and a lower bound. And for bounded real sequences, we can define two very special limit points called lim sup and lim inf. And one way of defining lim sup and lim inf is to say that lim sup is the maximum limit point, and lim inf similarly is the minimum limit point. So for example, in this picture, the maximum limit point is A, so A is lim sup, and the minimum limit point is A prime, so A prime is lim inf. Now, there are two things I want to point out about this definition. I guess the first thing to be pointed out is that the fact that these are real sequences is quite essential, because the notion of maximum and minimum requires us to be able to compare the elements in the set that we're working with, in particular the elements of the real numbers, which we can do, but in any metric space that may not be allowed. So the real part is pretty essential in even saying maximum or minimum of a set. And the second concern that you might have is that how do we know that maximum limit point is actually a thing? How do we know this actually exists? First of all, it's not really even clear, if it's your first time seeing this, that a limit point of a sequence even has to exist. And not only that, even if we imagine that there are a bunch of limit points, how do we know that there is a maximum one? And remember from the previous episode that if I give you a set, say a set of limit points, then the maximum certainly does not have to exist. So how do we actually know that this definition even makes sense? Well, it turns out that they actually can be justified, but rather than doing it directly, let me do that by giving you a second definition of lim sup, and I leave it up to you to think about what the corresponding second definition of lim inf is going to turn out to be, and this second definition is going to allow us to pretty easily show that maximum limit point actually exists. The trick is to consider the following set. So first I'm going to consider the terms of the sequence as a set, and I guess it should be pointed out that this is not quite the same as the sequence itself, because for example, if the sequence turns out to be 1 2 1 2 1 2, and so on. Then when I make it into a set, then the set gets rid of duplicate, so we only get 1, 2. And notice that because this thing is bounded, in particular bounded above, we know we can take the supremum. And when we take the supremum, let's say we get b sub 1. And now what we're gonna do is I'm gonna get rid of a1, and I'm gonna start at a2. So let's consider a2, a3, a4, and so on. And then after that, let's get rid of a2, and let's consider the set a3, a4, a5, and so on. And again, all of these are going to be upper bounded, so we can take supremum. So we have b sub 2, then b sub 3, and we can continue this process. And now there is something to be realized about b sub 1, b sub 2, b sub 3. I claim that these is monotonically decreasing and bounded below. So remember a while ago I defined monotonically increasing, monotonically decreasing is defined in exactly analogous way. So I'm just saying we have this chain of inequality. Well, why is this true? Well, remember the supremum is the least upper bound of the set, and here all I'm doing when I go from b sub 1 to b sub 2 is I'm getting rid of some element of the set. So when I consider any upper bound for a1, a2, a3, and so on, in particular its supremum perhaps, then this is certainly still going to be an upper bound for this set. So when I take the least upper bound of b2, then b2 is going to be smaller than b1. And you can continue this line of logic to show that it only goes down. And why is it bounded below? That's simply because each b1, b2, b3 is an upper bound of some subset of the set of the terms of the sequence, and the terms of the sequence is bounded below. Remember that the sequence is bounded, so in particular it's bounded below, so that certainly forces each of the b's to be bounded below as well. And the reason we care about this is, remember, when I have a sequence that's monotonically increasing and bounded above, then that sequence converges to supremum. Now, in an totally analogous way, and with the same proof, if I have a sequence that's monotonically decreasing and bounded below, that's gonna approach the infimum. So we know this b is going to approach the infimum, so let's say it's going to approach b, and this limit is by definition, so by definition, we're going to call this lim sup of a sub n. Let's try to get some intuition over this definition and see why we in fact should get the maximum limit point. So again, if I have this picture that we were considering before here, then let's think about what b1, b2, b3 are. Well, what is b1? That is supremum of all the points in the sequence, and that's clearly a1. That's in fact the maximum. So in this situation illustrated here, we get a1 as b1. And what about b2? Well, b2 is supremum of every term except a1. So we get rid of a1, and you take the supremum of what's left, and that's clearly a3. That's the maximum. And then b3 is supremum of a3 and so on. And this is certainly still going to be a3, but it's not too hard to see that as we continue doing this, the supremum is going to shrink as in the following. Initially it's a1, then it's going to become a3, then it's going to become a5, and we continue to have this kind of dropping in supremum, and we see that the limit is a, which in fact is the maximum limit point in the scenario. So that seems to be good. Now just to get even more intuition, I want to consider a slightly different sequence. So let's say our a sub 1 is here, a sub 2 is here, then our odd terms, so a sub 3 is here, a sub 4 is here, and if you look at the odd terms are going to approach a from the left. So I'm going to have a1, a3, a5 approaching a like this, and a2, a4, a6 can still approach a prime, that's fine. In this case, this definition of lim sup still pick up a. In this case, what happens? Well, b1 is supremum of everything, and what is supremum of everything? Well, it's not hard to see that the least upper bound for the sequence is in fact a. So we get a here, and b2, even if you get rid of a1, well, it's clear that supremum is still a. And in fact, in this case, it's not too hard to see that all the b sub n is going to be a. So we just get a constant sequence converging to a. So in both of these situations, we in fact seem to be converging to the maximum limit point. So now let's actually show this. So the claim I'm making here is that this is actually the maximum limit point. So this is the claim. Well, for this, there are two things to show. First, I gotta show that this is actually a limit point. This is a limit point. And the second thing I need to show is that there are no limit points larger than lim sup. So let's actually try showing this, starting with 1. So to show that using the second definition of lim sup that it's a limit point, we want to show that there is a subsequence of a1, a2, a3 that's converging to b. How can we find the subsequence? Well, let me start by giving you a slightly incorrect proof, which has all the right ideas with one subtle error, and we're going to fix that very soon. And here's what we're gonna do. So we have the real line, we have a b somewhere here, and we know that these b sub 1, b sub 2, b sub 3, that this sequence of supremums is decreasing and converging towards b. So we have something like this happening, b1, b2, b3, and so on, converging to b. Now what do we want? Now we want a subsequence of a1, a2, a3 that's actually converging to b. So how do we find this? Well, I'm going to use a classic proof technique in real analysis where we're going to consider distance of 1, then 1/2, then 1/3, then 1/4, then 1/5, and so on. What we're gonna do is we're gonna first find some a sub n1 that's within distance of 1 from b. Then I'm going to find a sub n2 that's within distance of 1/2 from b. Then I'm gonna find a sub n3 that's within a distance of 1/3 from b, and so on. If I can find this subsequence such that the distance from b is within 1, then 1/2, then 1/3 in this manner, then it's easy to show that this thing in fact has to converge to b. If that's not obvious, I encourage you to pause the video and think about why that's the case. So to find such a subsequence, here's what I'm gonna do. And maybe one is this big. So this is our initial epsilon. And now we want to find some a sub n1 within a radius of epsilon from b. So we want to find some a sub n1 inside here. The first thing to use is the fact that b is the limit of the sequence b1, b2, b3. So we can actually find some b that lies within this epsilon radius. So we can, for example, in this picture it's b2, but in general there's always going to be some b sub n. So locate that. And now what I'm gonna do is I'm going to go back. I'm going to go back a tiny bit, say epsilon over 2 distance. So maybe this distance is epsilon divided by 2 from b2. And now think about what's happening within this interval. Well, because b2 is a supremum, so I mean in general it can be bn, but the b2 is supremum of some subset a2, a3, and so on. In particular, it's the least upper bound. And since we went backwards the distance of epsilon over 2 from b2, we know that this purple point going back a distance of epsilon over 2 is not an upper bound for a2, a3, a4, and so on. So that's telling us we can locate some a sub n1 that's within epsilon over 2 of this b2. And it should not be too hard to reason that this a sub n1 is within distance of epsilon of b. So we got a sub n1 and we just repeat. For a sub n2, just do the same thing, but starting with epsilon of 1/2, and locate some b sub n, go backwards epsilon over 2, and then we can find some a sub n2 within epsilon of b, and we continue this process to find the subsequence. And it seems like we're done. Why doesn't this, what's the error in this proof? Well, the only error is we gotta ensure that n1 is less than n2 is less than n3 and so on. After all, if we find n1 using this argument, maybe that happens to be larger than the n2 we find using this argument. Even as epsilon is shrinking, what's really guaranteeing that our n's are always strictly increasing even towards the start? Well, here's how to fix the argument. When we're trying to find a sub n2, we want to pick n sub 2 such that n sub 1 is smaller than n sub 2. And we still have this property that a sub n2 is within 1/2 of epsilon. How do we do that? Well, when we go through with this argument, say with epsilon of 1/2 here, we first gotta locate some b sub k lying within epsilon of b. And something we can do, because b sub k's are just decreasing towards b, just converging to b, we can in fact guarantee that the b sub k we pick here, so the b sub k we pick for epsilon of 1/2, we can guarantee that k is strictly larger than n1. Because as the index in b sub k is increasing, we're only getting closer and closer to b, so we can certainly wait until the index is larger than n1 to pick this b sub k. And once we found the b sub k, remember that we went back distance of epsilon over 2, and we found some a sub n2. And how is this a sub n2 found? Well, b sub k here is the supremum of the set containing the terms of the sequence starting with a sub k. So if we use that supremum argument of going back epsilon over 2 and finding some element of the set that's larger than this b sub k minus epsilon over 2, then certainly a sub n2 we're going to find is still going to satisfy that n sub 2 is larger than n1. In fact, this n sub 2 is going to be greater than or equal to k, so we can satisfy this inequality, and we just do the same thing from a sub n3. So that justifies 1. How do we show 2? That there is no limit point larger than lim sup? Well, let's suppose that's not the case. So we again have the real line. We have our lim sup lying here, and let's say we happen to have some b prime that's strictly larger than b. That also happens to be a limit point. So we have some subsequence an1, an2, an3, and so on that's converging to b prime. Now, to get a contradiction, we'll take a look at b sub n1, then b sub n2, and so on. And remember, b sub n1 is defined to be the supremum of a sub n1, then a sub n1 plus 1, and so on. So, in particular, b sub n1 is going to be larger or equal to a sub n1. So we know b sub n1 lies somewhere to the right of a sub n1. And similarly, b sub n2 lies somewhere to the right of a sub n2. And similarly for b sub n3, and so on. And here something to be pointed out is that the picture here is a little misleading in the sense that maybe a sub n1 could have started to the left of b, then a sub n2 is still to the left of b, but the point is because this subsequence is converging to b prime, eventually the terms of the subsequence are going to be located strictly to the right of b. And because of that, by discarding the initial terms and just taking the tail of the subsequence, where you're still converging to b prime, but everything is to the right of b, so that this picture actually makes sense. And once we actually have a subsequence converging to b prime, where all the terms are to the right of b, in particular, we know all of these, b sub n1, b sub n2, we know all of these are larger than a sub n1. So here what I'm saying is b sub n1, b sub n2, b sub n3, all of these are at least a sub n1, and this is strictly larger than b. But this is a contradiction because remember, what is b? Well, b is the limit of the sequence b1, b2, b3. This is a monotonically decreasing sequence that's converging to the infimum b. But what is happening in this picture? Well, if I consider epsilon small enough, and I consider this region of all the points within epsilon of b, such that b plus epsilon is less than a sub n1, then there has to be some capital N. So starting at some b sub capital N, all the terms of the b's have to lie within this neighborhood. But we have found this b sub n1, b sub n2, b sub n3 with n1, n2, n3 all increasing towards infinity, such that all of these numbers are lying here on the real line to the right of a sub n1. So we have found a contradiction. So a limit point larger than b, like b prime, cannot exist. So that verifies 2, and that justifies the fact that if we define lim sup using this definition, using the second definition, then we in fact have that lim sup is the maximum limit point. Having shown that, now let's think about whether we can get rid of this bounded condition for the real sequence. For example, consider the situation illustrated here, where we have our even terms of the sequence a2, a4, a6, and so on, still approaching a prime as before, but for our odd terms a1, a3, a5, and so on, all of these are, say, distance 1 apart, and they keep on moving towards the right, towards infinity, at a constant pace. In this case, you may suspect that we probably want to define lim sup such that lim sup is equal to infinity, because we literally have a subsequence that's growing without bound. And in some other situation, so perhaps this is some other situation, in which our sequence looks like this. Maybe we have our a1, and then we move 1 to the right, then we have a2, and then we move 1 to the right, then we have a3, and our sequence just goes off towards negative infinity at a constant pace. In this case, we don't have any limit points on the real line. The sequence is just moving towards negative infinity at a constant pace, so we don't congregate anywhere. So in this case, you probably suspect that we want to define lim sup to be negative infinity. In the light of these observations, one way of making all of this precise, and also pretty consistent with this limit of the supremum definition that we gave for the lim sup before, is to first define things like limit as n going to infinity of a sub n, so where this is a real sequence, is infinity, and also analogously when it's equal to negative infinity. Let's just do positive infinity for now. And this isn't too hard to define. Let me first give you the definition, then give you some intuition over it. So what this is going to mean is that for all, say, some positive real numbers, so for any positive m greater than 0, no matter how large this is, there is going to exist some positive integer n, such that a sub n is going to be larger than m for all n greater than or equal to n. So what I'm saying here is that if this is the real line, and say 0 is right here, no matter how large of an m that we select, so maybe our m lies all the way up here, then what we have is that we have some capital N, and let's just suppose for the sake of example that n happened to be like 1 million, such that starting with the millionth term, our a sub n is greater than m. So again, what might be happening is that maybe for the first million terms, our sequence is doing some strange things, but at least after the millionth term, our sequence is actually lying to the right of m. And here, of course, the key thing is that this capital M can be picked as large as we want. So we can also pick this capital M to lie way over here on the real line. And then maybe our capital N is going to increase to, say, a billion or something. But after a billionth term, now all of our terms of the sequence is lying here. And we can continue repeating this for any capital M. So it should be reasonably intuitive that this condition is essentially telling us that if I look at the terms of the sequence, then it's intuitively approaching infinity. Now, what about limit of a sub n being negative infinity? Well, in this case, we are just going to change the condition such that instead of a sub n being larger than m, let's just make it smaller than negative m. And now, given this, let's go back up and try to more rigorously compute lim sup of this sequence. And to do so, let's see what these b1, b2, b3 turn out to be for this sort of real sequence. Well, b1 to start is supremum of the set consisting of every term of the sequence. And here, because these terms are going off to infinity, it makes sense to say that supremum is positive infinity. So technically, we only defined the supremum for sets that are bounded above previously in the series, but if it's not bounded above, then it makes sense to define supremum to be just positive infinity. And it's not too hard to see that even if we get rid of a1, even if we get rid of this term, then the supremum of the entire thing is still positive infinity. And in fact, this persists throughout. Now, if we are defining lim sup as the limit of b sub n, as we did before, I guess you're in this position where you also have to define what it means for the limit of sequence containing positive infinity. But in this case, it's pretty obvious what the definition should be, especially considering that the b sub n we know is actually going to form a decreasing sequence. You know, this is monotonically decreasing. So either we're going to decrease to some real number that's less than infinity, or we're going to always stay in this positive infinity constant sequence, which is happening here. And in this case, we certainly should define the limit of this to be positive infinity. So we, in fact, as we suspect, that lim sup is positive infinity as desired. Now, one last thing I want to say about lim sup and lim inf is this important fact that limit of a sequence, so here let's say a sub n is a real sequence, is a if and only if lim sup and lim inf both agree with a. Now with the correct definition, you can certainly do this when a is actually positive infinity or negative infinity. But just to make things easier, let's just say here we're in a situation where our sequence is bounded. So it's a bounded real sequence, and here when I say a is actually an element of the real numbers. So how do we justify this? Well, the forward direction, so this direction, where if the limit is a, then lim sup and lim inf is equal to a. In my opinion, this is the easier direction, and I'll just leave this as an exercise, just for you to convince yourself. It should be pretty obvious, because if the limit of the entire sequence is a, then there really ought to be only one limit point, which has to be maximum and minimum limit point. So lim sup and lim inf has to equal to a. So that should really justify the forward direction. But I'll leave it up to you to write it out a little more rigorously. Now the backwards direction, which I think is a little trickier. So let's say we're in a situation where lim sup and lim inf both equal to a, but just the regular limit is not equal to a. So what I'm saying here is that even though this is true, it happened that this is not true. So we want to show that something goes wrong. And if something goes wrong, then limit actually has to equal to a here. So we justified the backwards direction. So what actually goes wrong? Well, let's reason. Here we have a real line. We have our point A somewhere on it, and we know by assumption the limit is not A. What does it mean for limit to not be A? Well, remember that limit being A, so this equality, is defined by the condition that for all epsilon greater than 0, there exists n, such that the distance between a sub n and a is less than epsilon for all n greater than or equal to n. So if limit is not a, then this entire thing, this part, existence of capital N satisfying this breaks. This goes wrong for at least one epsilon. So what we know is that there exists some epsilon greater than 0, because we're assuming limit is not a, such that if we consider this particular condition, so let's just call it star, such that the star, this condition is not met. Now, what should this mean on the real line? Well, let's consider the special value of epsilon. So we have some epsilon region here. So I'm considering all the points within epsilon of A. Now, what can we say about this interval? To begin with, we cannot have that all terms of the sequence, so A1, A2, A3, and so on, we cannot have that every term is inside this interval. Because if that's the case, then we can certainly pick this capital N to be 1. Because starting with the first term, all the terms are within epsilon of A, so everything works out. But we know this condition is not met, which is telling us that we can actually find some term, say a sub n1, that's lying outside this interval. So we know a sub n1 is gonna lie somewhere here. I just picked it to the right, but it can also be somewhere on the left of the interval. But now the important thing is we can continue this. So if I look at every term in the sequence after the an1 term, so if I look at all the terms starting at the index n1 plus 1, then in that case, not all of those terms can lie inside the interval, because if all of those terms lie inside the interval, then just pick this capital N to be strictly larger than n1, so that this starred condition is met, which cannot happen. So that's telling us that we can find some an2 such that n2 is larger than n1, and an2 also lies outside the interval. And continuing that line of reasoning, we can again find, say, some an3, then an4, and so on. So we can find a subsequence such that all the terms of the subsequence is lying outside the interval. And what is that telling us? Well, we're either going to have infinitely many terms of the subsequence to the right of this interval in this region, or we are going to have infinitely many terms of the subsequence to the left of the interval. And in the first case, the contradiction is going to come from the fact that lim sup has to equal to a, and in the second case, the contradiction is going to come from lim inf equal to a. More precisely, if you have infinitely many terms here to the right of this point, which is a plus epsilon, so we have this a plus epsilon, and we have infinitely many terms of the sequence here, then now the problem is if I consider the terms here as a sequence on its own right, so if I consider this like sub-sequence lying to the right of a plus epsilon, this sequence is also going to have its own supremum, and the supremum of this is going to be a limit point of this sub-sequence, and in particular it's a limit point of the original sequence. But that's telling us that we have a limit point larger than a plus epsilon. And we cannot have that because the maximum limit point of the sequence was supposed to be a, and that gets you a contradiction. And similarly, we get a similar contradiction if we have infinitely many points to the left of a minus epsilon. Let's move on. Now, one point that I want to quickly discuss in passing in this video is the notion of the limit of a function. So let's say we have some function from some metric space x to metric space y. Now all this notation is saying is that for each point, say p in the metric space x, so for each element p of x, our function is going to output some f of p, which is going to be a point in the metric space y. And let's say we have a situation like this. So just for the sake of simplicity, let's consider a function from real line to the real line. And let's say the graph of the function on the xy plane looks something like this. So here's the x-axis, here's the y-axis. And let's say our function looks exactly like y equals to x cubed. So let's say this is our function f of x is equal to x cubed. Except let's actually make one modification. Let's say at point x equals to 2, instead of outputting 8, which is what the function should output if it actually behaves like f of x equals to x cubed throughout, let's say we output some other value, say 4. So more precisely, I'm considering a function which is x cubed whenever x is not 2, and it just happens to output 4 when x is 2. Given this sort of picture, what the concept of the limit of the function is going to do. So if I consider limit as x approaches 2 of f of x, then this limit is going to capture the fact that if as we are approaching 2, and we just ignore what happens actually at 2. So what happens at 2 and f of x outputting 4, actually we don't care about that. But as we are approaching near 2, the function seems to be approaching 8. And the limit is going to capture that idea. And in this particular situation, the limit as x approaches 2 of f of x is going to be 8, because as x is approaching 2, but not exactly at 2, our y values, our function values, are approaching 8. And here's a way of making this notion precise. We're going to say that limit as x approaches a of f of x is b, where now a is some element in the metric space x and b is some element of the metric space y, if the following is true. So if I have any sequence, say x1, x2, and so on, converging to a, where here importantly, we don't really want to care about what happens when the sequence value is equal to a. So here we'll assume all x of n is not equal to a. So we have some sequence in x that's approaching a, but none of the terms actually equals a. And in this case, if the limit is b, what we're going to have is that if we look at f of x1, f of x2, and so on, so if I consider this sequence now in y, it's going to converge to b in y. So in this sort of picture, what we're saying here is that if I have a sequence, say x1, x2, x3, and so on, that's approaching 2, then if I look at the function values, so say f of x1 lies somewhere here, then maybe f of x2 lies here, f of x3 lies here, then these function values is going to converge as a sequence to 8. And the key thing is, no matter how we approach a, no matter what sequence we use to approach a, for all such sequence, we in fact have the corresponding function sequence going to b. It's not hard to prove rigorously that the limit of this function at 2 is actually 8. So let's quickly take the time to do so. So if I consider in this picture any sequence, say x1, x2, that's converging to 2, we want to show that if I consider the function sequence, which in this case, because none of the term equals to 2, we know we're considering x1 cubed, x2 cubed, and so on, and we want to show that this converges to 8. But that's pretty clear because we showed in the previous video that sequence behaves very nicely with respect to arithmetic operations. In particular, what we have here is a sequence given by xn times xn times xn. So this is the nth term of this sequence. And we showed in the previous video, if x of n converges to 2 and x of n converges to 2, then the product here of these two sequences is actually converging to 4. And we can just apply that one more time. We have a sequence converging to 4. We have a sequence here converging to 2. So when I take the product of these two sequences, then that's going to converge to 8. So that rigorously shows that limit as x approaches 2 of this function is 8. Just to add one or two more things, let's now assume that we have a function from R to R instead of just any metric space. And in this case, now it's also pretty easy to work with. Limit as x approaching infinity or limit of f of x being infinity. Users, instead of using a and b being any real number, we can certainly use a being infinity where our sequence is approaching infinity. And in that case, I guess you can drop the condition that x of n is not equal to a, or you can change b to infinity as well. So all of these concepts can be defined. And the one more thing I want to mention is left-sided or the right-sided limit. And to illustrate that, let's focus on this picture and let's assume rather than our function behaving like x cubed to the right of 2, we have something weird happening where our function is always constantly 4 to the right of 2. So if our f of x looks like this, then you may suspect that if we consider limit as x approaches 2 from the right, so this plus sign is meaning you're approaching from the right, and the minus sign, so like x approaching 2 from the left, is going to signify you're approaching from the left. And if we consider this limit of f of x, as we're approaching 2 from the right, the function value is always 4. We probably expect this to be defined to be 4. And that's indeed the case. How we can define that? So if you want to define limit as x approaches a from the right, all we have to do is, rather than having this condition that x of n is not equal to a, we just restrict it to x of n being strictly larger than a. And in this case, we're just approaching using a sequence to the right of 2, so this definition is going to make intuitive sense. And similarly, if we want a from the left, then we just change this to x of n being less than a. The very last thing I want to do is to talk about an extremely important relationship between Cauchy sequences and the convergent sequence. So we already know what it means for a sequence to converge. Now, what does it mean for a sequence to be Cauchy? Well, let's say we have some metric space X, and we have a sequence A1, A2, A3. In this case, we say that the sequence is Cauchy if the terms of the sequence are getting closer and closer to each other. So what I mean by this is that for all epsilon greater than 0, there is going to be some capital N, such that if you look at the distance between a sub n and a sub m, we're going to see that this is less than epsilon whenever both n and m are greater than or equal to this capital N. So there is some threshold, capital N, such that after this point, the terms of the sequence are very near each other. And a natural question to ask once this definition is posed is, what's the relationship between Cauchy and convergent? Now, one direction is pretty clear. If a sequence converges, then it is going to be Cauchy. And the reason, I guess I can illustrate this for the real line, although you can do this for any metric space, is that if I have some point A, such that our sequence is actually converging to it, and then after some point, if we look at a sub n and a sub m, we're going to see that this a sub m and a are going to be very close to each other, and a and a sub n are going to be very close to each other, and the triangle inequality should ensure that a sub m and a sub n in turn are very close to each other. A rigorous proof is exactly based on that intuition. So the point is that if our sequence a1, a2 is actually converging to a, then we can pick some capital N such that distance between a sub n and a is less than, say, epsilon over 2 for all n greater than or equal to n. And if that's satisfied, then certainly distance between a sub n and a sub m by triangle inequality is going to be less than or equal to distance between a sub n and a plus distance between a and a sub m. And then as long as this n and m are greater than or equal to this capital N that we chose here, this is going to be less than epsilon over 2 plus epsilon over 2 or epsilon. So the sequence is going to be Cauchy. Now the other direction, that a Cauchy sequence has to converge, this is actually not true in general. For example, if I consider the metric space Q, so this is just the rational numbers, and we can just use the Euclidean metric. So we can just use Euclidean metric to measure the distance between any 2 points in the rational numbers. I claim that I can give you a sequence of rational numbers that's Cauchy, but it does not converge. For example, if I consider something like log base 2 of 3, which is around 1.584, 9, and so on, and remember that this is irrational, the key thing to notice is that if I consider the sequence like 1, 1.5, then 1.58, then 1.584, so the sequence formed by cutting off the digit of this log base 2 of 3, each time one more to the right. In this case, this thing does not converge in Q. This thing does converge in R. In fact, it converges to log base 2 of 3 in R. But the problem is, if our entire metric space is Q and we only care about sequence and limits in Q, then certainly we're not converging to any value in Q because log base 2 of 3 is not in Q. But at the same time, because the sequence converges in the real numbers, we know it's going to be Cauchy with respect to Euclidean metric, and certainly Cauchiness still goes through in the rational numbers. So this thing is Cauchy in Q because, again, if I have a sequence just consisting of rational numbers, then the condition for Cauchy in Q and Cauchy in the real numbers is really the same. So this gives you an example of a sequence that is Cauchy, but it does not converge in a metric space. But you may suspect, looking at this example, that maybe Cauchy does imply convergent sequence in R. So if I consider the real numbers with the Euclidean metric, of course, it seems like at least this particular sequence does not give you a counterexample, and maybe this implication is true for the real numbers. And this is in fact true, and this is a famous theorem. And how it's expressed, so here's the theorem, is that real numbers is complete. And all complete means is that it's a metric space where Cauchy implies convergence. So that's just the definition of complete. So how do we show this? Well, to start with, let's say we have some Cauchy sequence A1, A2, A3. That's a real sequence. And now we want to find some real numbers such that this sequence actually converges to it. How can we do so? Well, to begin with, realize that the sequence is actually bounded. And that's really because it's Cauchy. In fact, any Cauchy sequence in any metric space is bounded. And that's just because if I consider the real line, we know there exists some capital N such that, say, distance between a sub n and a sub m is always less than 1 for all n and m greater than or equal to n. So in particular, if I look at a sub capital N, because the terms of the sequence are within one of each other after this point, we know if I consider the distance of 1 here, so this is 1 radius of an, then we know all the terms of the sequence after a sub n lies in this interval. Well, what's that telling you? Well, that's telling you that there are only finitely many terms of the sequence outside this interval. And if you have finitely many terms outside this bounded interval, then certainly the entire sequence has to be bounded. So we know Cauchy implies bounded as desired. And now, what do we know if I have a real sequence that's bounded? Well, we know there is lim sup on the real line. So we know there is some point A, which is lim sup of our sequence. And what do we know about lim sup? Well, we know it is a limit point. So we know there is a subsequence, say an1, an2, an3. So we know there is a subsequence that's actually converging to A. And now here's the observation to finish off. We have found some real number A, such that we have a subsequence getting closer and closer to A, and we know the terms of the sequence, since it's Cauchy, is going to get closer and closer to each other as n and m approach infinity. And you may suspect, using triangle inequality, that now the terms of the sequence is actually going to converge A, and that's the idea behind the proof. So to write it down a little more rigorously, what we want to show is that the distance between a sub n and A can be made as small as we want for all large enough n. And we just use triangle inequality to write it as a sub n minus a sub nk, where a sub nk is a term in the subsequence converging to A, say plus a sub nk minus A. And now what do we know? We know for large n and large k, we know by Cauchiness that this thing can be made as small as we want, say less than epsilon over 2. And we know because a sub nk converges to A, by making k large enough, we know this part is going to be less than, say, epsilon over 2. So just by picking n and k large enough, we can ensure that for all n large enough here, we in fact have that this entire thing is less than epsilon. So that shows that our sequence is actually converging to A, and implies that for the real numbers, Cauchy implies convergent, or that R is complete. It deserves to mention one easy extension of this theorem, and that's that if I look at Rn under the Euclidean metric as usual, then this is also complete. I can do the proof for R2. The proof is of course exactly the same for Rn. And here, let's say we have some Cauchy sequence, say A1, B1, A2, B2, and so on. So this is a Cauchy sequence in R2. We want to show this converges. To do so, remember from the previous video that a sequence in R2 converges if and only if the first coordinates converge in R and the second coordinates converge in R. We showed that in the previous video, and in using exactly the same idea, it's easy to show that this thing is Cauchy in R2 if and only if the sequence A1, A2 and the sequence B1, B2 are both Cauchy in R. This is pretty easy to show, and these two sequences are going to be Cauchy in R precisely if it converges in R, because R is complete, and if the coordinates are converging in R, then that's exactly going to imply that our original sequence is going to converge in R2. So that finishes the proof for R2, and for Rn, you just do it for n coordinates rather than 2 coordinates. Anyway, I think that's all I want to say in this episode. I will see you in the next episode, where we're going to start doing more topology by introducing notions such as open and closed.